Symmetry and group theory. We have already seen that allowed spectroscopic transitions are determined by selection rules, and the selection rules are based upon term symbols. However, molecular term symbols can be difficult to determine. For example, even a simple diatomic, the relative energy levels are based on electronegativity and are difficult to determine beforehand. For multinuclear molecules, the resultant term is a linear combination of other linear combinations, which is also difficult to know beforehand. Therefore, we turn to the role of symmetry in group theory. Since a molecule is a linear combination of linear combinations, the resultant solutions retain the symmetry of the original functions. Symmetry elements are grouped. Having one symmetry element ensures having several others. Therefore, once one finds one point of symmetry on a molecule, one can determine much about how it's going to behave spectroscopically. Symmetry has to do with how an object can repeat itself through space through various manipulations. Therefore, there are several symmetry elements to consider. First of all, there are 3 axes and 3 planes of physical space, as you know. There are the x, the y, and the z axes that all things exist on. And these form the xy, xz, and yz planes of space. An object may be symmetric on one axis, on one plane, or on multiple combinations of any of the above. The various iterations and options available are what make up the symmetry elements. The first symmetry element is a rotational axis, symbolized by the term C sub n. Basically, one looks at, can an object be rotated within a plane around a particular axis without changing its shape? Can an object reproduce itself when it's rotated within a plane? If so, how many rotations will it take? This is the value of n in C sub n. Let's look at a couple of simple shapes to see how this works. First of all, a square. If you take any corner of a square, you can see that it can be rotated 90 degrees in order to produce an identical image. Since an entire rotation is 360 degrees, and you only have to turn 90 degrees, 360 divided by 90 is 4. Therefore, a square has a C4 axis of rotation. Another common shape is an equilateral triangle. Any vertex of the triangle must be rotated 120 degrees to produce the identical image of another equilateral triangle. In other words, 1/3 of a circle. So 360 degrees divided by 120 degrees equals 3. Therefore, an equilateral triangle has a C3 axis of rotation. Finally, let's look at a circle. A circle can be rotated by any amount to produce an identical image. An infinitely small angle will give you a circle again. Essentially, infinitely small means 360 divided by essentially 0 degrees, which is infinity. Therefore, a circle has a C infinity axis of rotation. The next major symmetry element is called a mirror plane, symbolized by the Greek letter sigma. A horizontal plane, sigma sum h, exists. This means, will a plane perpendicular to the main C sub n bisect an object? A vertical plane, sigma v, also exists, meaning, will a plane containing the main C sub n axis bisecting object. We will again look at our three basic shapes: a square. It can be seen that a square has 4 sigma v planes, remembering that the main axis of rotation, the C4, is coming from essentially above the page to the middle of the circle. And the square can be cut in half 4 different ways. As a two-dimensional shape, there are no sigma horizontal planes because there is no depth to the image. Therefore, a square has 4 sigma v planes, but no sigma h planes. Next, an equilateral triangle. An equilateral triangle can be cut in half 3 different ways, coming from each vertex to the center of the opposite side, since that means it has 3 sigma v planes containing the reference C3 axis. Again, as a two-dimensional shape, it can't be cut in half horizontally. It has no depth, so there are no sigma h planes. Therefore, an equilateral triangle has 3 sigma v planes, but no sigma h planes. Finally, a circle. A circle has infinite number of sigma v planes containing the reference axis C infinity. You can cut a circle in half at any given point and have equal halves. As a two-dimensional shape, there is no horizontal plane. Therefore, a circle has an infinite number of sigma v planes, but no sigma h planes. A third symmetry element is called a center of inversion. Can an object be pulled through the central point to reproduce itself? Once again, by example, what is meant by this? Start with a square. As you can see from the previous slide, a square has the center of symmetry. Therefore, if one attempts to invert the square by pulling each point through the center to its opposite point, one finds upon inversion that one reproduces a square that maintains a center of symmetry. Therefore, a square inverted through a central point produces an identical image, and therefore, a square has I, a center of inversion. If one looks at an equilateral triangle, again, from the previous slide, one sees that an equilateral triangle does indeed have a center of inversion. However, upon a center of symmetry, upon inversion, pulling each point through every other point on the opposite side, what one finds is that one now has an inverted triangle. Inverting an equilateral triangle through a central point produces a mirror image of the original, and therefore an equilateral triangle does not have a center of inversion, I. Finally, a circle. Again, from the previous point, circles do have centers of symmetry. Therefore, if one wished to perform an inversion, drawing any point in the circle to its opposite point through that center of symmetry, one will find that one produces a circle that still has a center of symmetry. Hence, a circle inverted through a center of symmetry produces an identical image, and a circle has a center of inversion. A final symmetry element is called an axis of improper rotation, S subscript n. This is rather complicated, as this is a compound action. It requires 2 motions. First of all, the object is rotated around the axis to produce a mirror image. Secondly, the object is then reflected through the plane perpendicular to that axis to return to the original image. It is important to note that only three-dimensional objects may contain an axis of improper rotation. From a chemical consideration, consider methane, with 109-degree separations between each hydrogen. Methane is a three-dimensional object existing on the XYZ axes, where roughly one hydrogen is to the right of center, one is to the left, one is projected in front, and one hydrogen is projected to the rear. Now, if one were to turn this 90 degrees around the z-axis, one would find the following. Upon the XYZ axis, you would have the methane molecule still there, rotated around the carbon. However, it is now inverted, with the left and right carbons below the XY plane and the front and back carbons above the XY plane. That is the first step to produce the inverted image. Now, if one was to reflect this image through a mirror plane, again, existing in the XYZ plane, you would see a methane molecule, and that molecule is now in its original form. Since a 90-degree turn was required to produce the mirror image, and 90 degrees is 1/4 of 360 degrees, methane has an S4 axis of improper rotation. It has been determined that different objects can have several different types of symmetry, either an axis of rotation, an axis of improper rotation, a mirror plane, a point of inversion. Therefore, symmetry elements can be related to each other. For example, consider a rectangle. Upon a 180-degree turn, what one finds is another rectangle. This indicates that the rectangle has a C2 axis. However, the effect is the same as reflecting through a sigma V plane. Also, this gives the same thing would have happened. This gives the same result as turning through a center of inversion. These relationships allow various elements of symmetry to form groups. Mathematically, a group is a self-contained set such that a combination of any two elements in the group produces a third element in the same group. No combination of any two elements in a group can produce a third element that is not in the group. Groups of symmetry elements are called point groups because the action of any element in the group will reflect any point of an object back upon itself. All point groups must also contain the identity operator, another symmetry function signified by E, to be complete. Essentially, performing the identity does absolutely nothing to the object. This is required because all shapes remain unchanged if nothing is done to them. Therefore, any shape can be in any group. While all this might seem overwhelming, it's actually a simple decision tree to determine what point group a molecule belongs in. Through VESPR, molecule shapes can be determined. These shapes have defined symmetries. Group theory allows all molecules, therefore, to be grouped by theory. So, for example, select a molecule. Ask a question. Is this molecule linear or is it not linear? If the answer is yes, then ask another question. Does this molecule have a center of inversion? If the answer is yes, it is a D infinity H group. If the answer is no, it's a C infinity V group. However, if the molecule is not linear, the next question, do you have 2 or more C sub n's rotational axes with n greater than 2? Again, if the answer is yes, the next question, do I have a center of symmetry? If the answer is no, you have a tetrahedral point group. If you think about it, you have just described a methane molecule. If the answer is yes, the next question, do you have a C5 axis of rotation? If the answer to that is yes, you have an icosahedral group, I sub H. If the answer is no, an octahedral group. Going back, if you do not have 2 or more C sub n's with n greater than 2, the next question is, are there any rotational axes present? If the answer is no, you then ask, are there any mirror planes? If the answer to that is yes, you have a C5 point group. If the answer is no, you then again ask, is there a center of inversion? Where a yes answer means you have a C sub I point group, and a no answer means you have a C sub 1 point group, essentially something with no symmetry. However, if the answer is yes to a C sub n, the next question, select the C sub n with the highest value of n. Then ask yourself, are there n C2s perpendicular to that C sub n? Again, yes or no answer. If the answer is no, do I have a horizontal symmetry plane, a plane of symmetry perpendicular to the C sub n? If the answer is yes, I have a CNH point group. If the answer is no, you then ask, are there n vertical mirror planes? If the answer to that is yes, you have a CNV. If the answer is no, you ask yourself, are there axes of improper rotation of S2n? If the answer is yes, it is an S2n point group. If the answer is no, it's simply a C sub n point group. Going back to the molecule of the highest n, and are there n C sub 2s? If the answer to that is yes, you then ask, are there sigma horizontal planes? If the answer is yes, you have a DNH point group. If the answer is no, you then ask, for those n C sub n planes, are there n dihedral planes? And n sigma d, meaning a plane with 2 simultaneous twists in it. If the answer is yes, if the answer is no, you have a d sub n. If the answer is yes, you have a d sub n sub d. We will now test this flowchart with a test case of ammonia. Here is the ammonia molecule, and the first question, obviously, is this molecule linear? The answer is no. Second question, does it have 2 or more C sub n's of n greater than 2? In this case, we try to rotate the molecule. By rotating 180 degrees, we find out we have a mirror image. We go from 2 hydrogen atoms facing forward and 1 hydrogen atom facing rearwards to 1 hydrogen atom facing forwards and 2 facing backwards. Continuing with ammonia. We already saw that ammonia wasn't linear, and by rotating the molecule, we found out it did not have 2 or more C sub n's of n's greater than 2. So, the next question, does it have a C sub n axis at all? The answer to this is if one rotates ammonia by 120 degrees, you have a mirror image with each hydrogen atom being displaced by 1. Therefore, the rotation of ammonia by 120 degrees produces the same image. 360 divided by 120 is 3, and ammonia has a C3 axis of rotation. Continuing with ammonia, we've seen the molecule was not linear. We've also seen it did not have 2 or more C sub n's with n greater than 2. But yes, there is a C3 axis. So now, the next question to ask, to select that C3 axis, are there 3 C2s perpendicular to the main C3 axis? This would involve a rotation of the molecule 90 degrees in the YZ plane. The result of which you see is an inverted image, where the lone pairs of electrons go from the positive quadrant to the negative quadrant. We have so far seen the ammonia molecule, seen it was not linear, that it did not have 2 or more C sub n axes of n greater than 2, but on the other hand, there was a C sub n, a C3. Within that C3, however, there were not 3 C2 axes perpendicular to the C3. So the next question is there a horizontal mirror plane? Putting a plane through the YX axis perpendicular to the Z rotational axis, one finds in inverting through the mirror that one gets an inverted image of the molecule, where once again the electrons move from the positive quadrant to the negative quadrant. So the answer to this question is no, there is not a sigma H plane. Continuing on, we've seen that ammonia is not linear. It does not have 2 or more C sub n's of n greater than 2. However, yes, there was a C3. In looking for 3 C2s perpendicular to the C3, one found the answer was no. It was also found that the molecule does not have a mirror plane in the horizontal axis. So the next question, does ammonia have a vertical mirror plane? One can see that 3 points defining a plane. If one starts with the point of a plane on each individual hydrogen atom, you can indeed, through a plane in the YZ, the XZ, and the XY, bisect the molecule 3 different ways, vertical to containing the C3 axis. So therefore, ammonia does have 3 sigma V planes. So reviewing our test case of ammonia, we determined that it is not linear. It does not have 2 or more C sub n's with n greater than 2. However, it does have a C sub n. There is a C3. Further on the logic tree, there were not 3 C2s perpendicular to the C sub n. Also, there was not a horizontal mirror plane containing the C3. However, there was a vertical mirror plane. Therefore, we have determined ammonia is in a C3V point group. Why is this symmetry important? Remember, molecules are linear combinations of atomic functions that have symmetry. Atoms are linear combinations of hydrogen-like wave functions that have symmetry. All functions, therefore, are based upon other functions that have mathematical parity and symmetry. Since symmetry is fractal, functions derived from symmetric functions retain symmetry. This might seem confusing, except for the fact that symmetry is a binary function. A function is either symmetric or asymmetric. This allows for simple yes or no relationships upon symmetry transitions. This, in a simplified way, leads to a series of matrix resultants, where a value of 1 means no change, therefore the operation was symmetric. A value of -1 means an opposite change, meaning the function was antisymmetric. For more advanced studies, other options are possible, 2s and 3s. This results in a character table for each point group. A character table is a matrix derived from the resultants of other matrices. Spectroscopic calculations are based upon the matrix operations of cross products. In order to gain an understanding of the meaning and the implications of what we've been talking about, let's look at a real character table. The C3V character table, which is the character table of ammonia. The first column in this character table contains the group sets for each space group. Functions in group A are functions where rotation around the principal axis is symmetric. Functions in group B are functions where rotational around the principal axis is asymmetric. Functions in group E are doubly degenerate functions where there is an inversion sensor, or symmetric operations to produce no change in sign. Functions in group T are triply degenerate functions where there is no inversion sensor, or symmetrical operations produce a change in sign. The last column contains the functions within each space group. In other words, functions for which these operations are true. Orbitals within a molecule are also functions. One may notice in the columns, x, y, and z are the axes upon which the p orbit lies. X squared minus y squared, z squared, xy, yz, and xz are d orbitals. So for example, if you look, x squared plus y squared and the function z squared are in the group A1. In other words, they are symmetric when being rotated around the axis, which goes back to the fact that 2 squared gives the same result as minus 2 squared, and you get a symmetric function upon inversion. Continuing to look at the C3V character table, one finds from the right, any given character table has the next to last column, planes of rotation. For example, linear movements in RZ require circular movements or plane polarization in the XY plane. Second to last column, linear movements along the axes identified. The remaining columns are identified by the symmetry elements within each group. The numbers in each column represent the resultant of a symmetry element upon each element of that group. We will now consider how character tables relate to spectroscopic transitions. A transition occurs in 3 steps and therefore has 3 symmetry elements. One has to consider the symmetry of the ground state G, the symmetry of the exciting radiation, lambda, and the symmetry of the excited state, E. In order to span a function, the resultants of the cross products of each action in order have to match the symmetry of the desired function. So for example, the symmetry sets in the ground state G individually crossed with the symmetry sets in the excitation radiation lambda crossed with the symmetry sets of the excited state E must equal the values in E1. Matrix operations are not commutative, they are linear. This means the ground state cross the excited state, cross the exciting radiation, cross the excited state, taken in the order that one crosses the ground state with the exciting radiation first, versus the ground state cross the radiation, cross the excited state, taking in order the ground state crosses the cross product of lambda and the excited state, are not equal. Also, unlike multiplication, the resultants of cross products are binary. In the first case, an example of 1 cross 1, are these two elements identical? The answer is yes, so your answer is 1. A state of -1 crossed -1, are these two elements equal? The answer is once again yes, therefore the resultant is 1. A symmetry of 1 cross -1, are these two symmetry elements identical? The answer is a no, so you get a -1. So far, this seems to be behaving just like multiplication. Another example, a symmetry element of 2 crossed with a symmetry element of 1. These two elements are also not identical. Therefore, by not being identical, the answer is simply a -1. What does all this mean? As always, the math matches or actually defines reality. For example, spanning A1 means every point group contains an A1 character set. Every box in the A1 character set contains a value of 1. This means every single shape contains at least one axis or plane that is unchanged under every symmetry operation. One or more orbital may lie on any given plane or axis. The requirement that a transition must span A1 means the symmetry must be maintained upon transition. Simply put, a transition cannot change the shape of a molecule. It cannot change its being. It can't change a duck into a swan. The non-commutivity of cross products. What does this mean? It matches reality. If you remember, transitions occur sequentially. An electron starts in the ground state. It then absorbs radiation. And after absorption, it is then promoted to the excited state. By not commutating, cross products simply follow the natural sequence of reality. How does this actually work? How can this be used? How do all of these symmetry elements help with spectroscopy? Let's look at a real-world example from the C3V group, which contains ammonia. Can radiation rotationally polarized around the z-axis, RZ, induce an electronic transition in an electron in ammonia from a pz orbital to a dx squared minus y squared orbital? One starts by looking at the character table and finding all three elements. First, the symmetry of the ground state. The pz orbital is in the A1 character set. The symmetry of the exciting photon. Photons that are rotationally polarized around the z-axis lie in the A2 character set. And the symmetry of the excited state. The dx squared minus y squared orbital is in the E character set. We will now use cross products and the character tables in order to answer this question. Shown here are the character sets for each of the ground state, the excited radiation, and the excited state. So the question is, do the character sets from the ground state cross the character sets for the excited radiation, with the result of that crossing the excited state span A1, or all answers 1? First, what is the cross product of the ground state, which has an A1 symmetry, crossed with the excited state, which has an A2 symmetry? For the A1 symmetry ground state, the characters are in the E character set 1, in the C2 character set 1, in the sigma V character set 1. For the A2 character set for the exciting radiation, the E character is 1, the C2 character is 1, and the sigma V is -1. Taking the cross products of each of these gives a resultant. In the E character set, 1 cross 1 gives a resultant of 1, which is placed in our character table. For the C2, 1 cross 1 also gives a resultant of 1, which we place again in our character table. For sigma V, 1 cross -1 is a -1, which gets placed in the character table. You see, this does not span A1, it actually spans the character set A2. After this, the resultant of this, A2, is crossed with the character set for the excited state, which is in the E set. So the cross products, for the A2, the characters are, the E character is 1, C2 also has a value of 1, sigma V has a value of -1. For the excited state E symmetry, E has a value of 2, C2 has a value of -1, and sigma V has a value of 0. Taking the resultants, for the E character set, 1 cross 2 is not identical and gives a resultant of -1. 1 cross -1 is not identical and gives a resultant of -1. 1 cross 0 is not identical, and you get a resultant of -1. So your resultant is -1 in E, -1 in C2, and -1 in sigma V. This does not span A1, therefore, this transition is not allowed. Let's look at 2 other spectroscopic possibilities, fluorescence and phosphorescence. The exceptions to the symmetry and the selection rules, essentially. In any spectroscopic transition, the energy of a photon is absorbed to excite an electron to a higher orbital, lambda excitation. The electron eventually falls back down to the ground state, emitting the energy that it loses as another photon, lambda EM, or lambda emission. For UV visible spectroscopy, absorption and emission occur simultaneously and continually. Therefore, the excitation wavelength is always equal to the emissions wavelength, and both processes happen virtually simultaneously. However, for fluorescence and phosphorescence, simply, absorption and emission do not occur simultaneously for reasons that you will see. Therefore, the excitation wavelength is not equal to the emissions wavelength. In real world, this is how some objects glow in the dark. First, we look at fluorescence. As you recall from your study of bond vibrations, chemical bonds exist in a potential energy well. Every bond has various vibration levels within that well. Bonds at higher energies are also further away from the nucleus, and their wells lie higher. These bonds also have vibrational energies. In the ground state, most electrons occupy the V equals 0 level. Therefore, electronic transitions start from the ground state in the center. transitions are linear on the energy axis. They start at the center of the energy well and then end wherever they intersect the next highest level. Since they are now in a higher vibrational state before falling to ground, these electrons must now vibrationally relax back to the lowest vibrational state. This is called internal conversion. Emission therefore travels a shorter distance than excitation. Hence, the wavelength of excitation is no longer equal to the wavelength of emission, and the vibrational relaxation in the excited state, which causes internal conversion, also causes the emission to be delayed by 10 to the minus 6 to 10 to the minus 9 seconds. Another type of delayed emission spectroscopy is called phosphorescence, where we'll start with the same two orbitals that we had for fluorescence. One in in the ground state, one in the excited state, with all their vibrational levels. Normally, selection rules forbid transitions between states with different degeneracies, E equals 3 versus E equals 2, and so on. However, bond vibrations periodically change the shape of molecules. When this happens, the point group the molecule is in changes, and formally disallowed transitions are allowed. Specifically, as the molecule vibrates and changes shape, bonds move in relation to each other. Now, in mid-vibration, previously widely separated bonds can overlap. An electronic transition will still start from the center of the ground state. In the first excited state, the electron will still relax through internal conversion. However, when the electron intersects the wall of the third energy well, it can now fall into the well for this third orbital. This is called intersystem crossing. From there, in the third well, the electron still relaxes through internal conversion, and the emission again travels a shorter distance. Therefore, once again, the excitation wavelength and the emissions wavelengths are not equal. However, while this is going on, the bond is still vibrating. This lower excited energy state will move away from the first excited state. The electron is now separated and trapped until the next vibration when there is another overlap. Intersystem crossing causes emissions to be delayed from anywhere from 10 to the minus 4th all the way up to 100 seconds. Phosphorescence is what's used in many glow-in-the-dark applications.